Man, only 6 students. Ooh. So first item of business, students on average, you guys did very well in the first test. I'm very proud of you. You did great. I'll give them back on Tuesday or Wednesday because I gave a few people some extensions. So I'll hand them back on Wednesday. But does anybody have any questions about anything before we start? I'm kind of hungry right now. Oh, so now what I kind of hopeful for this. Anybody have some favorite fast food? What's fast food? What's your favorite fast food item? Last class it was an Oreo McFlurry. Is that another good one, or does someone have another idea?
McDouble.
McDouble. All right. We got the McDouble. All right. Let's see if Siri, how many calories are in a McDouble?
I found this on the web for how many calories are in the MC double.
MC double. That sounds like a, yeah. Just 370? I thought they were bigger than that.
That sounds about right.
So 370 calories. Does that mean that every single McDouble you get has 370 calories? No, it's probably more something like this. With a distribution, and the peak of that distribution is 370 calories. But you're going to have some McDoubles that are 350, some that are 390, right? It's not going to be too surprising. Not every single one is going to have the same number of calories, some sort of distribution. Where I'm going with this is I want to talk about this in terms of gases. So I'm going to I'm building up kinetic molecular theory, and one of the general postulates of gases is, and I've said this, the average kinetic energy is proportional to the temperature of that, in this case Kelvin, but the average kinetic energy of gases is proportional to its temperature. But just like McDouble, McFlurry, whatever you want to have, there's not going to be the same number of calories in each. There's a distribution. And just like in gases, there's going to be distributions of temperatures. And although this is I drew this as a very Gaussian curve, it's a little different for gases. I'll show you. It's a little heavier at the origin. But kinetic molecular theory is also the theory that it's the perfect gas theory. This is what the ideal gas law is based off of. So kind of like if you think, what's your ideal person, your ideal partner, the male or woman or whoever you're in a relationship. I guess I should. In my evaluations, I said it says I have to be more not hetero. I have to say heteronormality, whatever spectrum you are on. But here's the perfect gas. The size of the particle of the gas is negligibly small. So the gas has a volume, but what makes up the gas has absolutely no volume whatsoever. And this is not a big deal until we get to real gases. The average kinetic energy of the particle is proportional to temperature, I said that. And the collision with one particle or another or the walls is completely elastic, meaning they don't stick together. There's no attraction and no loss of energy. So Okay, here, just like the McDouble, here is a distribution of gases, and so here on the y-axis you see the velocity. Oh, this is not full screen. Sorry about that. Y-axis the velocity, x-axis y-axis is number, x-axis is velocity. So velocity is just the same as speed, but velocity has a direction. So like moving north is positive 100 meters per second, and moving south is negative 100 meters per second. So, okay, so you can see here, here's oxygen. Oxygen is 32 grams per mole, and lighter than that is nitrogen, 28 grams per mole, water 18, helium 4, hydrogen 2. So the heavier gases, their distribution is more bunched up, and the lighter gases is much more broad. But the idea is the area underneath the curve, each one of these is the same for the same number of gas particles. And another thing to note, there's a bunch up here in the origin, meaning there are some really cold gases, so meaning they don't move very fast at all. But on average, these all have peaks. See these peaks, and these peaks here, this is the root mean squared velocity, and we'll do a problem about that real soon. Those peaks, root mean squared, and I don't know why chemistry uses U. I always thought its velocity is V, but the chemistry uses U for velocity. So the root mean squared, you take the root of the mean of the velocity squared. So why do you square the velocity? Because it can be negative. So how do you get rid of a negative? You square it. So and the velocity for all gases, it's a real number. I mean, if it was I, if it was like 3I or some complex number, then if you square that, you could get a negative number. But all the velocities for all at least, you know, like in this reference frame is a real number. So it can be negative by direction, but it's not an imaginary or complex number. So you square it, all the negatives become positive. And you take the average of that, and then you take the square root of that. And you get the root mean squared velocity, which is the points at the peaks. And what else is saying? I'll show you another picture. But gases, they fly around. I only have two hands, but so gases are always flying around. And you might have one that's moving slowly, and then it gets hit by another one. That one transfers the momentum. Now this one's moving slowly. Or maybe you have two fast gas particles. They slam together, and then they lose their momentum, and now they're moving slowly, and then another one hits it. So at some point in time, the gas particles are all flying around, slamming into each other. And with that, you have that huge distribution. Plus, it's also changing. Each gas particle is changing its velocity because it keeps on hitting into things, hitting into the wall, hitting into each other. Okay, and let me go to the next one, temperature. So here we have all the same temperature. Now we have gas. Here's nitrogen at different temperatures. So this is nitrogen, and you can see here x-axis is velocity still, and y-axis is number. And these are the same amounts. The area under the curve is all the same number of particles. But the lower temperatures have a very narrow distribution. The medium temperature has a medium distribution. A high temperature has a very broad distribution. And so what? Why do we care? Not this semester, but if you go on to take 162, you learn about something called activation energy. So activation energy, that's about the energy it takes to start a chemical reaction. So, well, before I get there, has anyone ever seen really old paper, like paper that's like 1,000 years old? Have you ever gone and seen something like a Gutenberg Bible? No, you haven't. Some people said yes. So what did it look like? Old, was it color? Yellow. It's like it was burning, right? It looks kind of like it got burnt, but not burnt that much. It's because it actually is burning, but it's burning slowly. So paper is pretty much sugar. It's mostly cellulose, and so cellulose, it's made of atoms, and atoms have an electron cloud around it. So if you have your paper and you have an oxygen molecule, so this surface here is all negatively charged. Oxygen has a electron cloud. So as oxygen gas approaches the paper, it slows down. And if it doesn't have energy, it just bounces right off. It doesn't get to touch the paper. So there has to be enough energy, there has to be enough momentum for the oxygen to be able to break through that electrostatic repulsion and then start to react with the sugar there, the cellulose, which is glucose, the sugar that's in the book. And so at 273 Kelvin, so about this temperature, there's a tiny fraction there. If you can see, I'm saying this. There's a little bit. I'm just arbitrarily drawing this line. There's a little bit, a few gas particles that have enough energy to react with paper at this temperature. But then if you look at 1,000 Kelvin, that's a little hotter than a candle flame. So a flame is at least like a match or a candle is about 600 Celsius, and that's about, I mean, more or less 900 Kelvin ish. So maybe at least the blue part of the flame is going to be hotter than 1,000 Kelvin. But either way, if you look at this part, there's a huge fraction, like about a third of the particles have enough energy to react with paper. So that's why you can have paper at this temperature for thousands of years, and it burns really, really slowly. Or you can take a match and light paper; it'll burn in the order of, a couple seconds, right? So a couple seconds to a minute, the paper's gone. And that's because at this temperature, there's gas particles with enough energy to break through that electrostatic negative barrier around the electron cloud. So also, we talked about vapor pressure of solutions. So that we said as you increase the temperature, there's more of a gas fraction above the water, or whatever solvent you have. I could use water. At a low temperature, so I'll just consider this line here to be the energy that it takes to break the water-water intermolecular, so between the two water molecules. So at a low temperature, there's a small fraction that has enough energy to break. So there's a little bit of gas in the vapor phase. And then at a medium temperature, there is a higher fraction. At a high temperature, there's an even higher fraction. So as you go up, there's more and more liquid particles. So the liquids work the same way. Solids too. Temperature works this way. It's a distribution. Not every single atom or molecule has the same motion, at least in the microscopic sense. And also want to be relative versus a zero reference frame. Like if I take this book and I throw it, it's going to have a velocity, and relative to the ground, this book is going to have a relative velocity when I throw it. But just sitting here, the atoms and molecules in this book, there's going to be a temperature distribution. It's not all going to be the same. And I know that for a fact because I just went swimming before this class, and you can feel cold spots in the pool or in the ocean, right? There's always a distribution. So I'm trying to connect this up with the stuff before with the vapor pressure. So you can see that, and as you increase the temperature, the distribution gets more and more broad. And again, this is going to be important later. We talk about kinetics. Oh, and the peak shift. That's the root mean squared velocity. It shifts to the right as you go into higher temperature. Okay, and that's done there. So we're going to see. So here's the derivation. I'm not going to go over it, but that's the effect. The root mean square velocity, I already told you that. And let's do a problem here. Calculate the root mean squared velocity of oxygen at 25 degrees Celsius. So there's two values of R. And one of the tricks for this one, you have to know to use the right value of R. So let me throw in the numbers. So there's the equation, square root of 3RT over molecular weight. So let's put it in 3. Then we have to do times 8.314 joules per mole Kelvin. I should do Temperature 25 degrees is 298 kelvins. All of our molecular weight 0.032 kilograms per mole. That's water, or not water, oxygen. So square root is to the half power, like so. So, and notice a couple things. Instead of saying 32 grams per mole, I said 0.032 kilograms per mole. And I raised it to the half power. Did you know that a square root is the same thing as raising it to the half power? I don't know if you guys know that. But, and like a cube root, if you can't find a cube root in your calculator, it's to the 1/3 power. And fourth root to the 1 divided by 4. But, okay, but let me show you why we're doing it this way because of units. So this is units dimensionality. So unit-wise, we have joules per mole Kelvin times Kelvin divided by kilograms per mole to the 1/2 power. So right, I'm just looking at the units there, and you can see the kelvins cancel, the 1/moles cancel. So we have joules per kilogram square root. And if you haven't had physics yet, that's fine. A joule, the units on a joule is kilogram meter squared per second squared. So the way I remember this is force is mass times acceleration. If you had physics, it's okay. You'll get the what a joule is. I'll give that to you. But so Newton's second law, force is mass times acceleration. Acceleration is the second derivative of displacement. So mass is kilograms. Acceleration is going to be length divided by time squared. So mass times length divided by time squared is force. Work is force times the path length. Force along the path length is work. So that means it's going to be the force kilogram or mass times length divided by time squared times length. So it's mass length squared divided by time squared, or by SI units, kilogram meter squared per second squared. So let me put that in there. This is then kilogram meter squared per second squared all over kilogram to the 1/2. And then the kilograms cancel, and we're left with meters squared per second squared square root, and that's meters per second. So the units, that's why this has to be in joules, that's why this has to be in kilograms. Okay, and you will be given this equation, you'll be given the different values of R, you'll be given the dimensionality of joules. I think I even put on there that you have to use kilograms for that one, molecular weight in kilograms. But you have to use that 8.314, not the 0.08206. Okay, but let's put the numbers in here for this one. So remember, it's about 500, if I remember correctly. 3 times 8.314 times 298 divided by 0.032. Yep. So this equals 482 meters per second. And you're like, what does that mean? That's really fast. So 480 meters per second. So that means a kilometer in 2 seconds and almost a mile in 3 seconds. Can you imagine moving so fast you can cover a mile in 3 seconds? That's how fast oxygen is moving on average. And it's not only that, it's a distribution. Right? It's going to look something like that. And then just this top here is 482. So it's You have some that are even moving faster. They're moving 5 miles a second or 6 miles a second over here. Or you have some that are barely moving inches every second. So it's a distribution. So the next question I get that people will say, well, that's faster than the speed of sound. I mean, moving a mile, 3 seconds to a mile, that's faster than the speed of sound. Why aren't we hearing sonic booms every second? It's because the air is what makes up the sound wave. And you need to have a bigger particle. So bullets can do a sonic boom. That's where the crack of a bullet comes from. You ever hear in the movies when they have the pew with the silencers? Like, no, they're still going to be, bullets are going to be loud no matter what because they're breaking the sound barrier when they're flying out. If you have a jet, if you have a bullet, and a crack of a whip, that's also breaking the sound barrier. You can, if that moves this speed, that'll do that. It'll make a sonic boom. But gas particle itself, no, it's part. First of all, a sound wave is the pressure going this way, the direction of the wave. You have to be a big enough particle to go through all that pressure wave. So the gas particles make up the pressure wave themselves, so that it doesn't matter how fast they're moving, they're not going to make the sonic boom. If that makes sense. Okay. So anyways, recap with this one. Use this equation, root mean squared velocity, have the right units, and then to get the proper answer. So, questions with this one? Nope. Okay. All right, so here is a typical gas path, and so here's a square box, and when I think of gas particles inside of a container, I think of like, pew, 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 they're flying, they're bouncing all over the place. Okay, so, and that's where the pressure comes from. The pressure comes from the sum of all the gas particles and hitting you with their momentum. So, right, if you hit me with one oxygen molecule, I'm not going to feel it, right? I'm like, what is that, kind of thing. If you hit me with a softball, that's going to hurt, right? That's a pretty big thing, though. An oxygen molecule is going to be about 10 to the minus 21 grams. That's about the mass of an oxygen molecule. Like a softball, it's about, 50 grams. So you hit me with that, going 100 miles per hour, that's going to leave, that might break a bone, kind of thing. So if you have so that's where the pressure, so if you have like a tank of gas, and you have gas inside the tank, that's where the pressure of the gas comes from. It comes from the collision of each of these gas particles. So a really slow-moving gas particle, so boom, 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 it's just the momentum, it's hitting it, so the mass times the velocity hitting the outside of the container. And if you increase the temperature, it goes pew, 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 pew. So it's moving, it has the higher temperature means more collisions because it's moving faster, so it can, assuming it's bouncing back and forth, I mean, of course it's bouncing all over the place, but if it's moving faster, it's going to have more collisions, and the collisions have more momentum. So the increasing the temperature will increase the pressure that way. The other thing, if you ever look at a gas tank, they're always roundish, right? So we have a propane tank out the side entrance here by the parking lot, and it's shaped kind of like a Tylenol. You know what I mean? It's like this. It's a cylinder with rounded edges, right? So you don't see gas containers shaped like boxes. Why is that? Because the pressure when the gas particles hit it, and when you have a gas cylinder, they expand. So they'll expand, and it can crack along the edges. So they're always going to be round shape. That's it's called the hoop stress. If you ever do in materials, so whenever you push on things like if I lean on the table, actually there's a handprint that appears in a microscopic sense on the table, and also the table's going to bend a little bit. It's not super sturdy. I mean, it's sturdy. It looks like it's not moving, but it's going to move. And in tanks, they move. And all materials, they bend and they flex a little bit. That's called the stress. The stress, and then the strain. It's how much it can handle. And if it's too much, they can either deform permanently or it can snap. So metals, the same thing works with stretching actually. So if you're stretching, they wonder why, like I can stretch further than this, but I want to be able to talk. You have to hold stretches for a while because it's got to deform your muscles. So you got to hold it for a while, because if you just like, oh, touch my toes, nope, see, that's fine. You have to hold on to it for a while so that then you actually tear the fibers a little bit to get them to stretch more. Well, you shouldn't say you don't tear; they just extend their whatever they go past their ultimate stress that they can spring back. It's their spring constant. Anyways, back to chemistry. So here we have the gas particles, and they're bouncing around. Same thing in gas, just the plain old gas. They don't necessarily, I'm showing this here hitting the sides of the container, but they're also hitting other gas particles. So it's not just the container, it's the other gas particles. And the momentum of the gas particles times the number of gas particles, that's the pressure. So that's where you feel it. And so what? Well, talk about next a phenomenon called a fusion. So if you have a gas particle or particles inside a container, and then there's a hole in them, the gas can't fuse into the empty space. It doesn't even have to be empty space, it's just lower pressure. So like, you ever seen like the balloons, you ever the helium balloons and they float? They don't float forever, right? They start to lose their helium, and then they start to get droopier and droopier. Why is that? Well, there's little tiny cracks in them. And over time, I mean, it's not a perfect, like those metallic, shiny-looking balloons, they last for a long time. They really do. But like the rubber balloons, if you fill this up with helium, they're gone in like a half a day or a day. They don't last very long. So, and that's just because there's little tiny holes and the gas seeps out. And we also know this from our tires. So, right, your tire, mine's like 33 psi or something like that. So essentially double atmospheric pressure. So the pressure inside the tire is about 3 atmospheres. So 1 from the atmosphere, 2 from the pressure inside there, and the outside pressure is 1 atmosphere thereabouts. And the tires deflate over time. Every once in a while, I have to go to the gas station and put a couple of psi into my tires, because your car runs better. It runs more efficiently when your tires are at their maximum amount. Not so much a big deal here in Hawaii, but if you live on the mainland, you have to put air in your tires in the winter. You have to bleed the air in the springtime. Otherwise, in the air in the winter, because it tends not to get flat, but it doesn't work as well when it's lower, when it's not as inflated. In the springtime, if you don't bleed the air out, your tire might blow up or rupture, so kind of thing. But we can separate gases this way. So we can, of course, have gases leave the annoying part of this is we have gases leave our tires and or floaty balloons. But on the good side, we can separate 2 different gases. And this is also how we enrich nuclear fuel. One of the ways to enrich nuclear fuel. I'll talk about that in a second. So let me do this for Graham's law of fusion. So, and the rate. So the rate of gas A over rate of gas B is the square root of the molecular weight of B over the molecular weight of A. So that's because the speed of A is 3RT over molecular weight of A. The speed of B is 3RT over the molecular weight of B. And so it's 1 over, and the 3RT cancel because the same temperature. 3 is a constant, R is a constant. Temperatures, assuming the same temperature, which makes sense if you have 2 gases together, you mean the same temperature. And so then it's 1 over m of A, 1 over m of B, and so then they flip and form that way. And let's do this. So an unknown gas diffuses at a rate that's 0.462 times that of nitrogen gas. Calculate the molar mass of the unknown gas. So the rate of A. So the rate of unknown is over rate of nitrogen is 0.462 equals let's see here, this is going to be then 28 grams per mole all over our unknown. I'm just using x as the unknown, square root of that. So I'm just applying this equation through the rate of unknown over rate of nitrogen is 0.462 equals 28, square root of 28 over our unknown. So that means you can square both sides. 0.462 squared is equal to 28 over x. Or when I see this, I just flip these. I put x here and I put that one down there. Is that too fast for you guys? Did you want me to move slowly? Raise your hand if you want me to. Okay. So you can multiply both sides. You can multiply both sides by x, and you get x times 0.462 squared equals 28. And then you can multiply both sides, or you can divide both sides. 0.462 squared. 0.462 squared. Then you get x equals 28 all over, because when you divide here, these will cancel there. 0.462 squared. But if you want, another way you can do it though is you can picture it doing math this way. Kind of go like that if you want to do it in your head. But I already know this is equal to, it's 131, which makes you wonder if it's xenon. So, because xenon's 131 grams per mole. So you look at the period. I don't think there's numbers on that one. I can show you this one here. I guess you probably can't see that. It's 131.3. Okay, so recap for this one. Graham's law of fusion, rate of A over B is the square root of B over A. So if the rate of A is 0.462 over 1, it's going to be 0.462 over 28 nitrogens over our unknown. Can then solve for the unknown being 131 grams per mole. So, questions with how this works? Nope. Okay. So why do we care? Well, it's how we can enrich uranium. So if you look at uranium, they were faced with this and when they were building the atomic bomb. The boiling point for uranium is 3,927 degrees Celsius, so 4,000-ish Celsius. That's really hot. So not surprising, it's really hard to boil uranium. It's pretty hard to boil most metals, except for maybe mercury. So, and one of the ways you can do it though, I don't know what boiling, I think it's like around 30 degrees, 30 or 40 degrees. Let's see. What is the boiling point of uranium hexafluoride?
Here's what I found on the web for what is the boiling point of uranium hexafluoride.
Okay, well hit Wikipedia, see what they give it the boiling point. That's the melting point, boiling point. Okay, 56 degrees Celsius. Oh, really? Oh, it sublimes. Oh, that's nice. Sublimes at 56. It sublimes before it melts. That's interesting. Either way, so 56 degrees, you can turn uranium hexafluoride into vapor versus 4,000 degrees for the metal. And so the way nuclear reactions work, it's the odd numbers. So uranium-235 is the nuclear fuel. Uranium-238 is also known as depleted uranium. So in a regular nuclear reaction, uranium-238 is not gonna fizz. It's not gonna engage in nuclear fission. You can get 238 to fizz. You have to use a fast neutron though. That only happens in the case of a really huge nuclear device. It's like the Minuteman ICBM missile that we have. That's like a 25 megaton yield, or the Tsar bomber that Russia has. That's a 50 to 100 megaton yield. But uranium-238 in general doesn't do anything. We use it for armor-piercing bullets, like the tank rounds and stuff like that. We use it for that. But not used as a nuclear reaction. Uranium-235, though, when you dig uranium out of the ground, it's 0.7% uranium-235, and for civilian nuclear power plants, we enrich it to 3 to 9%, and for atomic weapons, we enrich it to 98, 99%. And so what? Well, that's how we get nuclear power and how we make nuclear weapons. And if you look at Iran, they found uranium enriched to 20% in their enrichment facilities, and we in the United States said, "Hey, you're making atomic weapons," and they're like, "No, we're not. We're doing it for peaceful purposes." And let me put it this way: either Iran hates money and they're galactically stupid, or they're making nuclear bombs. So let me explain. So a civilian nuclear reactor is going to be something on the order of 4 to 8 times the size of this desk. Okay, so they're not that big. I mean but I mean the whole reactor itself, just the core of it, is relatively small-ish. I mean it's the size of 2 or 3 compact cars, and it's also not that hot. A nuclear reactor, we typically run them at about 500 degrees Celsius. And a candle flame is about 600 degrees Celsius. So a candle is hotter than a nuclear reactor. Why? Because we can get it hotter, but we don't want to, because then it melts down, right? So you like to keep nuclear reactors kind of low temperature. I mean, and that's in 500 degrees Celsius. That water boils at 100. So I mean, that's plenty of energy. So if you put more uranium-235 in the fuel, it's harder to control it. So you have to have more safety things in place. So if you're going to run a nuclear reactor, you want it to be lower fuel than higher fuel, because it's more dangerous to have higher fuel. It can get hot too quickly, and it can have a runaway chain reaction. And the other thing is, it takes a bunch of energy and money to enrich uranium. So you're going to build a nuclear reactor that's more dangerous and has more safety equipment, and the materials cost more, or you can just stop enriching your fuel. I mean, of course, you're going to stop at a lower concentration because it's safer, it's cheaper, and it's easier to manage. Now, a nuclear sub's reactor core is about it's like 2 liters. It's really small. They use weapons grade uranium in that. Why? Because they have a space limitation. It's submarines if the core is only a couple liters, versus a couple thousand gallons, I mean, which is still pretty small for a power plant. And of course, there's always stuff around it, right? So the civilian plants, they usually have it in water. So, and then there's all the tubes connected to it as well, the generator, that kind of thing. Same thing in a Navy ship, except everything's more compact. That's why they use super enriched uranium. So, but if you're going to have a civilian nuclear power plant, why would you enrich it that far? It would be stupid. You have no problem with space. I mean, having something the size of 3 cars,
who cares? You can, like, you look at the windmills. I mean, that's the size of, like, several trucks, right? So why would you worry about space? So that's why we're like, Ron, you're making nuclear weapons. Like, no, we're not. I love that the president said there's no gay people in Iran either. Whatever. Okay, so how much faster does it diffuse? So it's going to be the diffusion of the lighter over the heavier. So it's going to be 238 plus 19 times 6, this quantity, over 235 plus 19 times 6. Both, I guess I don't need the square root of that. I guess I don't really need the parentheses over that. I guess I'm reminding myself that because I need to do that in my calculator. 2 parentheses 238 plus 19 times 6. 235. So it's 1.004. So yeah, it doesn't go that much faster. So even with this, I mean, doing that small, it's still hard to separate them out. So what they do is they have centrifuges, and has anyone ever been to a brewery before? No one has. Jeez. No one in the last class did either. They're usually a big room full of stainless steel tanks, really big stainless steel tanks. That's what a brewery typically is. At least it looks like to me. If you ever go to a place like that and you hear this kind of sound, and especially if you see like yellow powdery stuff around, uranium hexafluoride, it's called yellow cake because it's yellow and powdery. You're probably in a nuclear enrichment facility. Just turn around and get the heck out of there as fast as you can. So, or you might say, that's a nice brewery. Okay. So, if you look at, so that's what uranium Iran's doing. They're making uranium bombs. So North Korea, they have some nuclear weapons. They're not very good nuclear weapons. So their engineering is pretty bad. They're pretty dirty though. They don't have a very big yield, but they're very dirty. So they're using plutonium. It's much easier to make a plutonium bomb than a uranium bomb, but at least, so like Iran is saying like, oh, we're making it for civilian use. There's actually civilian use for uranium. North Korea is just outright, we've made bombs. Well, I think they're not going to make any more plutonium, but they've made it for nuclear weapons. With plutonium, you can separate plutonium from uranium chemically. I don't know exactly what it is, but like one will dissolve in hydrochloric acid, one won't, kind of thing. So you can take the fuel rods, soak them in HCl or some other, maybe it's nitric acid, I don't know. It'll strip out the plutonium and then you can precipitate it down. And then you can make the weapons from that. So it's much easier to get plutonium than it is uranium, at least to weapons grade. The other thing about plutonium, so critical mass for uranium to make a nuclear weapon is about 50 kilograms. So that means you need uranium about the size of like a small beach ball. It's like a basketball medium beach ball sized of uranium. Plutonium, it's 5 kilograms. So it's like softball. So they have plutonium nuclear grenades. I don't know that have a yield of like 5 kilotons. So like 1/4 of the Hiroshima bomb. So those are Cold War relics. I don't know. If you pulled the grenade, yeah, you could throw something. So 5 kilograms, that's what, 11 pounds. I mean, you could throw that, right? You know, but you know, what hole could you dive under, you know, before that thing goes off? But so you can make them pretty small. And but the problem with plutonium is that it has a really high rate of spontaneous fission. So with uranium, every once in a while you'll have a spontaneous fission event, and then neutrons are given off, and then those neutrons are absorbed by nuclei, and those split, and that's how the chain reaction happens. Same thing with plutonium, but it's too fast, so you can get to what's called fizz. It means it's too fast, and then you don't get a very high yield. So you have to take the sphere, you have to compress it down to the critical mass. You have to do it in a very exacting way. Otherwise, it won't work. So pretty much all of the bombs that North Korea have tested, they've all fizzled in one way or the other. And they say they've made a hydrogen bomb, but I used to be a nuclear scientist. I don't think they did. I think they created it was called a fusion boosted device. If you put tritium, so hydrogen with 2 neutrons, in with a plutonium bomb, you get a fusion boosted device, and you increase the yield that way. I mean, a hydrogen bomb, it's really big. It's like, I mean, on the order of like 5 megatons. It's a huge explosion. So I think they did it. Either they have, and if they did make a hydrogen bomb, it would be the crappiest hydrogen bomb in the history of humanity. But I mean, mind you, they're still, I mean, it's no joke. The nuclear weapons are scary. But the ones that they have are not any stronger than like a really big bomb. But I mean, like our nukes or Russia's nukes or China's nukes, I mean, those will wipe out cities. So like if they blew one up, at Krispy Kreme, we'd probably be okay here for North Korea. So it would be a really dirty fallout. You would the shockwave wouldn't kill us, but the radioactive fallout might kill us. So I mean, we don't want to be hit by them. But it's not like, you know, it's not like, you know, United States warfare weapons or other nuclear power warfare weapons. So, and I hope they don't get there. But yeah, how are we doing? Any questions so far? Any questions about nuclear stuff? I love nuclear science. Nope. Okay. All right. So I'm not going to test you on this, but I do want to talk about it. I'm not going to test you about nuclear weapons either. I've never seen one go off. I think that would be cool, but then again, well, I guess I wouldn't want to see one go off because that could, you know, they do hurt you. But so here is our ideal gas. So we have different gases here, and the y-axis is the volume. So the ideal gas, perfect gas, should have a molar volume of 22.4 liters. And you can see that none of them are the same except for helium. Helium is about the most ideal gas you can get. And you have hydrogen that's a little bit more. So why is hydrogen a little bit more? Well, depending on the temperature, it can break apart and form 2 particles. So that's why it could be a little bit more. But the reason why these are a little bit less is because there's an attraction that they have for each other. So because of that, it seems like the volume is less than it should be. And helium, like I said, is the most perfect gas there is. Helium is a strange substance. So the distance in liquid water is about 300 picometers. Between 2 water molecules in liquid water is about 300, 300 times 10 to the minus 15, so 3 times 10 to the minus 13 meters. So, and helium, in solid helium, it's 500 picometers. So it means, and the reason why molecules is an attraction, they stick together. So helium just doesn't really like itself. It just wants to be left alone and sit by itself, kind of thing. And there's some debate amongst the scientific community if helium actually has a liquid and or solid state because of that. So that's above, of course, above and beyond this course. But this is where your tax dollars go to, is having people, well, not like me anymore, but back when I was in grad school and postdoc, go to conferences and talk about, I didn't talk about this, but listen to people talk about helium and it's maybe what state it's in. But anyway, so real gases, this is the non-ideal behavior. So at high pressure, remember the ideal gas has the particles themselves have no volume. But if you get under really high pressure, so then the particle's volume come into play. So here's argon gas or some other gas, real gas. And if the pressure is increased, the molecule and or atom's size come into effect, and the volume is slightly bigger than you'd expect. So that's at high pressure. At low temperature, the gases get sticky. So at low temperature, the pressure is lower than you'd think it would be. So here, so the xenon, it's going to have an attraction to itself. And as it's attracted, it's going to kind of, it's the two gas particles will be like one because they kind of stick together. And because of that, we have a lower volume than we would expect. Or lower pressure, sorry. Well, that'd be a higher volume. But anyways, lower pressure than you would predict because they're sticky. And so this was formed the van der Waals equation. Again, I'm not going to test you on this. And truth be told, this is a really bad way to deal with real gases. So there are much better ways to deal with real gases. There's something called K's law, where you put a z in front of there. So you have a fudge factor you put in there, and then that changes. There's a table of it. Say, okay, for this temperature and pressure, use 0.3, and then it changes. But another one, there's data, there's real data in things called the Cox charts, COX charts. So you can use real data rather than using fake data. And there's also semi-empirical models called like the Antoine equation. But that's more of an engineering application. This is derived from the ideal gas law, the van der Waals equation. The idea is, so PV equals nRT, and then you have this correction factor. So correction factor there for the intermolecular forces, and correction factor for the particle volume there. And it's not even a really good way to do it. The other ways work better. So, and here's the constants for the gases there. There's tabulated ones. And the worst thing about this equation is it's really hard to solve for n. So if you wanted to solve for like temperature, that's okay. Volume, oh yeah, volume and pressure, yeah, you could solve for pressure. That wouldn't be too hard. Solving for volume or solving for n, especially n, that is really hard. You have to do what's called an iterative technique. Has anyone ever solved by iteration before? No, you haven't. You have to do calculations over and over and over again until it converges. So it's best to use Excel for that. And just like, then copy the formula down a chart kind of thing. But you have to do it numerically. And I don't like doing it that way. So it's, like I said, it's much easier the other ways. But sorry if I'm dishing on this textbook. I like this textbook, but some of the things they do, I think is kind of stupid. But if I think it's stupid, why am I talking about it? Because it illustrates really well what non-ideal gas behavior is like. So it shows you that intermolecular forces and the particle volume kind of thing. So questions on real gases? Oh, okay. So I'm going to move on to chapter 6 then. I think the first class is going to go further than us. It almost always happens that this class moves faster. Okay. Anyways. So chapter 6 is thermo, intro to thermo. We are going to cover, so if you go into chemistry 162, there's a chapter in thermo there as well. We're going to cover an intro to thermo here, and we're going to have another intro to thermo in chapter, I guess it's 18 in the book, I think. But so in second semester. Second semester, we're going to talk about entropy and free energy. Okay, so entropy is disorder, and that things tend to become more disordered as time goes on. That's known as the second law of thermodynamics. And the third law, this defines entropy. We're going to cover in pretty much detail the first law of thermo. So, and again, is anyone ever taken a speech or is it speech or communications? I think it's communications, don't you call it? You have to take that class, don't you? Yeah. They always tell you don't ever apologize to the audience and don't tell them you hate your topic. It's like, I'm sorry, but I hate thermo. I don't like it. I'm more excited about stoichiometry than I'm the thermo. I hate thermo. I don't know why. I love quantum and bonding. I think that's a lot of fun. And kinetics. That's the fun stuff for me. But this stuff I think is kind of boring. But my students like it because it's pretty straightforward. So students tend to like thermo. But it's just not that much fun. The other thing about thermo is that a lot of it's already been solved. There's nothing really new and novel in thermodynamics. So I gotta be careful what I say. I'm gonna hate mail if people start listen to my YouTube stuff. But like quantum is still an emerging field of sorts. Although we understand it pretty well, there's still a lot of fine things that we've been tuning out with, or that we've been working on with quantum. Anyway, so energy in chemistry, we define it as the capacity to do work. Physics defines it as a force over a path length. That's a better definition, but you're saying capacity to do work. And two main forms, kinetic and potential. Everyone's awake, good, I don't want to scare anybody. So the classic high school physics example, this book has potential energy, and now it's turned into kinetic energy. So we've stored the energy, and then it's turned into another form of energy, but the energy is conserved. We have not created new energy. Energy is conserved. And the first law of thermodynamics is basically the conservation of energy. The internal energy of a system is equal to the work plus the heat that leaves or enters the system. So, and there's more terms in this one. Chemistry simplifies it. I mentioned gravitational potential energy. So water flowing downhill, that's also the first law of thermodynamics. So if you might see this in other classes that include things like gravitational potential energy. So like I said, water flowing like we have water towers up high, and you open up your tap and the water flows downhill. The pressure differential makes it go down. The pressure differential comes from gravity. So there's other terms in here, but we're going to simplify it to just work plus heat. So what do I mean? Internal energy change of the system. Now let me get back up. Is anyone in Calc 3 or 4 right now? No, okay. So anyone taken Calc 3 or 4? So no one's there yet. Okay. That's fine, that's fine. I had one student that in the last class. I occasionally get students. If you look at something like this is the partial differential, if you get this situation where the partial differential is exact, this is then known as a couple names. It can be called a state function. It can be called a mother function. It can be called path independent. So, or it can be called exact differential. That's the math term usually used as exact differential, which the consequence, it means it's path independent. So this one here, the internal energy, is in fact a state function. Work and heat, these are not state functions. These are path dependent. So what do I mean? I can take a gallon of gasoline and I can put it into like a big drum and I can light it on fire and it can burn and I can get no work out of it and I can get all heat out of it. So, and the internal energy of the gasoline burning in oxygen, it will be the same as if I take the gallon of gasoline, put it in my car, and then I get 20% work and 80% heat out of it. Or if I throw it into a hybrid car and I get like a third work and 2/3 heat, the energy that I get from using a gallon of gasoline, it's not going to change whether I just burn it and get the heat or I throw it into a regular car or a more efficient car, which means more work and less heat. The numbers will all be the same. So this is path independent, but these are path dependent. So same thing with sugar. Sugar burns. Has anyone ever tried to burn food before? Like Doritos make great kindling, so if you ever want to use potato chips, you put a match on it, those things light up really fast. So you can burn potato chips out in the air, or you can eat them, and we can burn them inside of ourselves. The fats and sugars in that, it's the same. If it goes through our mitochondria and by enzyme action, the citric cycle gets turned into adenosine triphosphate, and then that springs our biological functions. That energy that we get from burning the food that way in our bodies and our mitochondria versus burning them in the air and oxygen, it's the same thing. It gets the same energy released from food as we would that way. And we kind of intuitively know this because like if we burn things, so if we took sugar and we burned it, that's how we figure out calories. So the way that you figure out the caloric content of food is actually to burn it and to see how much energy you get from it. And that's why you see things like the artificial sweeteners. If you look at them, they have calories. So you look at like Diet Coke's got is it Diet Coke? There's just 1 calorie. I don't drink soda. That's an old one. But they have something small like 5 calories or something like that. Like, okay, how did they figure out this thing has 5 calories? Because they burned it. And they looked how much energy it released. But the question is also, by ingesting that, do I actually get 5 calories of energy from it? That's one of those. We don't know. But that's the way the labeling laws work. But, I guess that's a bad example because we don't know if our bodies can actually burn like saccharin. But sugar we can definitely burn. I know that from eating chocolate before I came here. So the change in internal energy is the same no matter what way you do it. So then we have path independent and path dependent. Okay, so the other thing about thermo is defining the system. The energy flow into the system is positive, and the energy flow out of the system is negative. So so positive and negative energy only matters by how you define the system. It's just the energy flow. So if I define the system as my body, and if I pick up some ice out of the freezer and I'm holding the ice, the energy flow is negative. If my body's a system, the heat is leaving my body going into the ice. Okay? If the system is the ice is receiving energy from me. It's going in the positive direction into the system. So does that make sense? So depending on what you define your system at, that's the direction of the heat flow or energy flow. And also, the energy leaving the system, this is called an exothermic process and or reaction. Energy into the system is called endothermic. So endo is inside therm energy heat. So inside heat is endothermic. Outside heat is energy leaving the system. So things that burn and get hot are exothermic, and things that get cold. So ice melting. So if you injure your arm and you have to wrap your elbow in ice, it gets cold as the ice melts. That's an endothermic process. And feeling something burn, you can feel the heat, that's exothermic. So we'll cover that more later, of course. All right, let's see. Last class didn't want to play with me at all. Let's see if you want to play with me. That sounds interesting. First law is change of internal energy is work plus heat. So 50 joules is our internal energy. Actually, I don't need the 50 joules. Equals work 20 plus our heat. So if the internal energy change is 50 joules, how much heat flow is on the inside? So how many people think B? All right, 100% is playing with me. Awesome. All right, so now, but I should say, anybody have any questions with this so far? Okay.
Is that right?
Yeah, that's right. I'm sorry. That is right. Sorry. Okay. Let me define some energy terms. So calorie. You've probably heard of a calorie before. A calorie is the heat to bring 1 gram of water, it's actually a liquid, up 1 degree Celsius. So a calorie, this is the energy it takes to raise 1 gram of water 1 degree Celsius. And nutritional calories, you see them, they're always capital C. So capital C calories. That is a kilocalorie, actually. It's going to be 1 kilogram water 1 degree Celsius. Or 1 gram of water 1,000 degrees Celsius. Of course, it'll boil away long before that. So when you have when you eat a 100 kilogram or 100 calorie chocolate bar, that's a lot of energy. I mean, you think about it. I mean, raising, like you put a kilogram of water, that's a liter. You put a liter of water in the microwave, how long is it going to take it to heat up? I mean, it's going to be in there for a long time. And so, I mean, 100 calories, I mean, that's a lot of heat. So it's a lot of energy. So I mean, food's got lots of energy. A lot of energy in that. So other units, though, has anyone ever heard of a BTU before? Yeah. Do you know what a BTU is?
British thermal.
Do you know what it's based off of, though? A calorie is 1 gram. Yeah. It's a pound of water, 1 degree Fahrenheit, is a BTU, British thermal unit. And maybe you've, especially if anyone heard of a ton, a TONNE energy unit? They usually sell them for AC units. They say it's a half ton or a quarter ton unit. Do you know what that is?
No.
A ton is 2,000 BTUs.
Oh,
So, and so a half ton AC unit, I think it's per hour. It means it will draw out a half a ton, so like 1,000 BTUs per hour. So that's a medium-sized AC unit. Like a quarter ton's pretty small. Half ton's normal size, I guess. So, but of course we use the metric system. Calorie is used frequently, and even more frequently for science is a joule. A joule, and we've also mentioned that's a kilogram meter squared per second squared. So a 1 calorie is also 4.18 joules. So if you ever go to a foreign country and look at nutritional information, some countries list their nutritional information in kilojoules. So I usually read the ingredient list and that kind of stuff on food. That's just something I'm just curious. I'm like, I had a bag of chips on the beach yesterday, and it was 210 calories. You know, I just wanted to see what it was, kind of. You know, and like if I used to live in Hungary, and the nutritional information was always in kilojoules. So if I wanted to know how much, like I do this if I'm like going to be away for a while or something like that, I'm like, oh, I need to get some food in me, and how much food do I need? I'm like, okay, I should get this many calories, or I wasn't really worried about getting fat or anything like that. I was just like, do I have enough food, kind of thing. And they gave me the answer in kilojoules, and I would just divide it by 4. So like, okay, so if it's 400 kilojoules, that's about 100 calories, kind of thing. So if you're ever somewhere and you want to know the difference, just, like I said, divide it by 4. So if you're in another country. Okay, and then now here's another equation. Heat, Q, heat, is equal to the heat capacity times the change in temperature. It can also equal to the mass times the specific heat capacity times the change in temperature. So this specific heat capacity is kind of like density. So if heat capacity is like mass, this is like density. So let me talk about heat capacity real fast. So things that have a high heat capacity means they can absorb a lot of energy and only the temperature will go up a little bit. So water, for instance, has a high heat capacity. If something has a low heat capacity, when it absorbs energy, the temperature goes up really fast. Or if it loses energy, the temperature goes down real fast. Metals have very low heat capacity. So I noticed as a kid, like if the sun was shining in the car and the sun was shining onto the seatbelt, and if you touch the seatbelt, it's really hot. But like I used to take the seatbelt and like put it on my arm, like, oh, that's really hot, and oh, it's not hot anymore, kind of thing. Because the high heat capacity, so it got a really high temperature, but it would just as soon as the heat left the metal, the temperature would drop real fast. So that's the low heat capacity. Whereas water takes a lot of energy to heat it up, and it'll hold on to energy for a long time. So water doesn't have the highest heat capacity. There are things that have higher heat capacity than water. Ethylene glycol, for instance, antifreeze, that has a higher heat capacity. So you ever wonder why we have antifreeze in our cars here in Hawaii? It's not going to freeze, right? We don't have to worry about the car freezing. Why do we have ethylene glycol in our cars? Because there's a higher heat capacity. So we can have a smaller radiator. So if you use water, you need to have a bigger radiator in your car. So we use antifreeze to keep our radiator smaller. That is also easier to just you have one type of car to have like can you imagine having a Hawaii/Southern California car or Florida car and then a Midwestern car? And they don't make cars perfectly. If you go to Alaska in the wintertime, you have to plug in your car. So they don't, because otherwise the engine will freeze up. It won't be able to start. And the fuel line might freeze too. But anyways. So heat capacity there, specific heat capacity. And how are we for time? Do we have enough time? I guess we have the time for this. So let me apply this for this next problem. Suppose you find a penny and you throw it in the snow. How much heat is absorbed by the penny as it warms from the snow, which is -8 degrees Celsius, to the body temperature of 37 degrees Celsius? So the mass is 3.1 grams, temperature, and it's copper. Okay, so we're going to use this equation. Heat is mass times specific heat capacity times change in temperature. So delta everything is always final minus initial. So your change of whatever is always final minus the initial. So if I had $40 in my pocket when I left the fair and I had $60 in my pocket when I entered the fair, how much money did I have? It was -20, right? So I lost $20. So final was 40 minus initial 60 minus 20. That makes sense. So change is always final minus initial. So in this case, it's 37 minus a -8, which is 45 degrees Celsius. So our Q is our mass, 3.1 grams times the specific heat capacity, which I don't know that for copper. Does anybody know the specific heat capacity for copper? Okay, where is it? Which is why I bring my book here. It is 0.385 joules per gram degree Celsius times 45 degrees Celsius. And doing all this, this is 53.7 joules. So this is actually not that much energy, 57 joules. I told you water has a high heat capacity. Water's is 4.18, so it's more than 10 times that of copper. So I guess if water has a high, it's more than 10 times. But anyways, here we apply this equation here, mass, specific heat capacity, change in temperature, and we get an energy change of 53.7 joules. Questions with that? All right, that's the shut up alarm. So I will be here if you have any questions. If not,